In 1945, I calculated something that most people still do not understand. Before we tested the first atomic bomb, a team of physicists ran calculations on whether the explosion might ignite the atmosphere. Nitrogen nuclei fusing with nitrogen nuclei in a self-sustaining reaction. The entire atmosphere burning. The physics was straightforward. Our bomb would create temperatures exceeding 10 million degrees at the core. At such temperatures, nitrogen nuclei have enough kinetic energy to overcome electrostatic repulsion. If nitrogen-nitrogen fusion released more energy than required to heat surrounding nitrogen to fusion temperature, a self-sustaining reaction would propagate through the atmosphere. Edward Teller raised this concern. Hans Bethe led the calculation team. They analyzed the reaction cross-sections, the probability that two nitrogen nuclei would fuse when they collided at given energy. They calculated energy loss mechanisms, radiation, expansion, convection. The conclusion? Nitrogen fusion would not self-sustain. Energy losses exceeded energy production. The reaction would quench itself. We determined the probability of error in this calculation was approximately 3 in 1 million, low enough to proceed. We accepted a 3 in a million chance of destroying all life on Earth because the alternative, Nazi Germany developing the bomb first, seemed worse. That calculation established a pattern. For 80 years, humanity has been accepting small probabilities of catastrophic outcomes. The mathematics of this approach guarantees eventual failure. Nuclear deterrence operates on a simple principle. If attacking guarantees your own destruction, rational actors will not attack. This logic contains a mathematical flaw. It requires perfect reliability over infinite time. Consider the arithmetic. Suppose the probability of accidental nuclear war in any given year is 1%. That seems acceptably low. 99% chance of safety each year. But probability accumulates. Over 10 years, 0.99 to the power 10th equals 90.4% cumulative safety. Over 50 years, 0.99 to the 50 equals 60.5% cumulative safety. Over 100 years, 0.99 to the power 100 equals 36.6% cumulative safety. With a 1% annual risk, nuclear war becomes more likely than not within 70 years. What is the actual annual risk? We have empirical data. Between 1945 and 2023, there have been at least 22 documented incidents where nuclear weapons were nearly launched by accident or miscalculation. Let me describe 3 with technical specifics. September 26, 1983, sensor physics failure. The Soviet Oko satellite system detected 5 American Minuteman ICBMs launching toward the Soviet Union. The system physics. Oko satellites carried infrared sensors positioned in Molniya orbits, highly elliptical paths that kept them over the northern hemisphere for extended periods. The sensors detected thermal radiation in the 2.7 to 4.3 micrometer wavelength band, optimized for rocket exhaust temperatures of approximately 2000 Kelvin. The detection algorithm compared infrared intensity against the cold background of Earth viewed from space. Rocket exhaust appeared as bright point sources moving against a dark background. Lieutenant Colonel Stanislav Petrov was duty officer at Serpukov 15. Protocol required immediate report to command. Soviet doctrine assumed American first strike would target command infrastructure. Delay meant losing retaliatory capability. Petrov judged the alert false. His reasoning was tactical, not technical. 5 missiles made no sense. An American first strike would require hundreds of missiles. He was correct. The satellite had detected sunlight reflecting off high-altitude clouds at a specific angle. Technical cause. The OCO sensors could not distinguish between 2000 Kelvin rocket exhaust and reflected sunlight at certain geometries. The sun's surface temperature is approximately 5,800 Kelvin. When sunlight reflected off ice crystals in high clouds, the spectral signature in the detection band could mimic exhaust. This was not human error. This was a systematic limitation of infrared sensor physics that had not been identified during testing. The false alarm occurred because physics does not distinguish between different sources of infrared radiation at the same wavelength and intensity. January 25, 1995. Radar signature ambiguity. Norway launched a Black Brant 12 research rocket to study the aurora borealis. The rocket reached 1,453 kilometers altitude. Russian early warning radar at Olenogorsk detected the launch. The radar signature resembled a Trident D5 submarine-launched ballistic missile. The physics of radar detection. Early warning radars measure the position and velocity of objects by timing the return of radio pulses. A rocket ascending through the atmosphere produces a characteristic signature: increasing altitude, specific acceleration profile, trajectory toward potential targets. The Black Brant 12 followed a nearly vertical trajectory. From the radar's perspective, the range, altitude, and velocity were consistent with a submarine-launched missile on a depressed trajectory toward Moscow. Russian military activated President Boris Yeltsin's nuclear briefcase. For several minutes, Russian command evaluated whether to launch retaliatory strike. The decision window for submarine-launched missiles is approximately 10 to 15 minutes, the time from launch detection to impact. This is significantly shorter than the 30 minutes for land-based ICBMs. Norwegian authorities had notified 30 countries in advance. The notification reached Russian diplomatic channels, but was not transmitted to military early warning systems. The physics was not wrong. The radar correctly identified an ascending rocket. The failure was that radar physics alone cannot distinguish between a research rocket and a weapon. Both produce identical electromagnetic signatures. November 9th, 1979. Digital system failure. NORAD computers at Cheyenne Mountain displayed a massive Soviet nuclear attack. Approximately 2,200 incoming missiles. Strategic Air Command prepared for launch. B-52 bombers started engines. Minuteman ICBM crews received preliminary launch orders. Within 6 minutes, satellite and radar data confirmed no actual attack. Investigation revealed a training tape simulating Soviet attack had been loaded into an operational computer. Technical cause? The training system and operational system shared hardware. There was no physical interlock preventing training data from reaching live displays. The computer could not distinguish between real sensor data and simulated data. Both arrived as digital signals in identical format. The display system processed whatever data it received. This incident prompted hardware redesign to physically separate training from operations, but it revealed a fundamental principle. Digital systems process data without understanding meaning. A computer cannot tell the difference between a real attack and a simulation unless explicitly designed to do so. These incidents reveal structural problems inherent to nuclear command and control. The detection decision time problem. An ICBM launched from Russia reaches the continental United States in approximately 30 minutes. The physics is simple. Ballistic trajectory with peak altitude around 1,200 kilometers, re-entry at approximately 7 kilometers per second. Submarine-launched missiles from close range arrive in 10 to 15 minutes. Depressed trajectories sacrifice range for speed. Current early warning architecture requires multiple confirmation steps. Satellite detection, 2 to 3 minutes after launch. Infrared sensors identify exhaust plume, but cannot determine target until trajectory becomes clear. Ground radar confirmation, 8 to 12 minutes after launch for ICBMs. Radar must acquire the target after it rises above the horizon. Assessment and communication, 2 to 5 minutes. Information must travel from sensor operators to command authority. Decision, unknown duration. The president must evaluate information and decide. Launch order transmission, 2 to 3 minutes. Orders must reach missile crews or submarines. For ICBMs, this leaves perhaps 10 to 15 minutes for decision. For submarine-launched missiles, perhaps 5 minutes or less. This timeline creates pressure to decide before confirmation is complete. Every false alarm occurred because the system demanded rapid response. The physics of ballistic trajectories imposes time constraints that cannot be negotiated. The sensor sensitivity trade-off. Early warning systems face a fundamental engineering choice. Infrared satellites can be calibrated for high sensitivity, detecting faint thermal signatures that might indicate launches, or high specificity, reducing false alarms by requiring stronger signals. High sensitivity increases the probability of detecting a real attack. It also increases the probability of false alarms from reflected sunlight, wildfires, industrial facilities, or meteorological phenomena. High specificity reduces false alarms. It also risks missing a real attack with unusual signature characteristics. System designers chose high sensitivity. Missing a real attack means destruction without response. A false alarm can potentially be corrected. From a game theory perspective, sensitivity is the rational choice. But this means false alarms are inherent to the design. They are not bugs to be eliminated. They are the mathematical consequence of optimizing for detection. The same trade-off applies to radar systems. High sensitivity detects objects at greater range and with less radar cross-section. It also increases false tracks from weather, birds, aircraft, and space debris. The automation dilemma. As delivery systems became faster, decision timelines compressed. Submarine-launched missiles from forward positions can arrive in under 10 minutes. Hypersonic glide vehicles further reduce warning time. This created pressure to automate response. The Soviet perimeter system, known as dead hand, was designed to ensure retaliation even if command authority was destroyed in a first strike. The physics. Nuclear detonations produce characteristic signatures. Seismic waves from ground bursts register on instruments worldwide. Radiation sensors detect gamma rays. Overpressure sensors measure blast waves. Perimeter monitors these signatures. If nuclear detonations are detected on Soviet territory and communication with command is lost, the system can authorize retaliatory launch without human decision. The logic is game theoretically sound. If deterrence requires guaranteed retaliation, and a first strike might destroy command before retaliation can be ordered, then automated response becomes necessary. But automation removes the human judgment that caught false alarms in 1983 and 1995. Petrov's tactical reasoning, 5 missiles made no sense, is not programmable. A machine cannot evaluate whether an attack is strategically plausible. Return to the mathematics. 22 documented incidents over 78 years suggests approximately 1 serious incident every 3.5 years. Not all incidents carried equal risk. Assume conservatively that 1 in 10 such incidents has a 5% probability of escalating to actual launch. Annual probability of serious incident, 0.29. Probability of escalation given serious incident, 0.05. Probability of launch given escalation, 0.5. Annual probability of accidental nuclear war, 0.29 times 0.05 times 0.5 equals 0.007. At 0.7% annual probability, 50-year survival probability, 70%. 100-year survival probability, 50%. 200-year survival probability, 25%. The actual numbers may be higher or lower, but the mathematical structure holds. Any non-zero annual probability accumulates to near certainty over sufficient time. After the war, I advocated for international control of atomic energy. This was not idealism. It was engineering analysis. Any system with non-zero failure probability will eventually fail. The only stable configuration is one where failure probability equals 0. 3 technical approaches could theoretically achieve this. Elimination requires verification that no weapons exist and cannot be quickly rebuilt. Current technology can detect operating reactors via heat signatures, enrichment facilities via electromagnetic emissions, and nuclear tests via seismic monitoring. It cannot reliably detect small stockpiles of separated material or disassembled components. Complete verification remains technically unsolved. Centralized control places all weapons under international authority. The Baruch Plan of 1946 proposed this. Technical problems remain. Enforcement mechanisms, capture by particular interests, authority to use weapons. Defense dominance would make nuclear weapons ineffective through reliable interception. The physics of missile defense imposes fundamental limits. An ICBM warhead in terminal phase travels at approximately 7 kilometers per second. An interceptor must achieve similar velocity and hit a target roughly 1 meter in diameter. Current ground-based mid-course defense has 44 interceptors with estimated 50 to 60% single-shot probability. Against a salvo of 100 warheads, defense would stop perhaps 25. 75 would reach targets. The offense can always overwhelm defense through numbers. Each offensive warhead costs approximately $50 million. Each interceptor costs approximately $75 million. And the offense can deploy decoys, balloons, chaff, maneuvering vehicles at a fraction of warhead cost. The physics favors offense. A warhead is a dense, heavy object traveling at 7 kilometers per second. An interceptor must find it, track it, and collide with it, all within minutes. The warhead needs only to survive. The interceptor must actively succeed. Defense dominance remains technically infeasible. The arms control alternative has been negotiated limits. Treaties constrained numbers and types of weapons. The peak Cold War inventory in 1986, approximately 70,300 warheads. Current global inventory, approximately 12,500 warheads. The United States holds approximately 5,500. Russia holds approximately 6,250. China holds approximately 410, projected to exceed 1,000 by 2030. The remaining states, France, United Kingdom, Pakistan, India, Israel, North Korea, hold approximately 1,000 combined. The reduction from peak is significant, but current arsenals remain sufficient to trigger nuclear winter. A single Ohio-class submarine carries 20 Trident II missiles with up to 8 W-88 warheads each. One submarine, 160 warheads, yielding approximately 76 megatons total. 8 Ohio-class submarines are typically deployed at any time, over 600 megatons at sea, invulnerable to first strike, capable of destroying any nation on Earth. What happens if deterrence fails? Modern nuclear war modeling uses atmospheric simulations validated against volcanic eruptions. The 1815 Tambora eruption injected approximately 100 teragrams of sulfate aerosols into the stratosphere, causing the year without a summer. Global temperature drops of approximately 1 degree Celsius. Nuclear weapons produce different particles. Burning cities inject black carbon, soot, into the stratosphere. Black carbon absorbs sunlight more efficiently than sulfate aerosols. Regional war scenario: India, Pakistan, 100 Hiroshima-sized weapons. Each 15-kiloton weapon ignites approximately 13 square kilometers of urban area. 100 weapons ignite 1,300 square kilometers. Burning buildings inject approximately 5 teragrams of black carbon into the stratosphere. Atmospheric models predict global temperature reduction of 1 to 2 degrees Celsius for 5 to 10 years. Growing season shortening. Agricultural yield reduction of 10 to 20% globally. Immediate deaths, 20 to 50 million. Secondary deaths from famine. Estimates range from 1 to 2 billion. Major power exchange. United States, Russia. 1,000 strategic warheads each. Modern strategic warheads yield 100 to 475 kilotons each. 1,000 such weapons ignite vastly larger areas. Soot injection. 150 or more teragrams. Atmospheric models predict global temperature reduction of 8 to 10 degrees Celsius for 10 or more years. This exceeds the temperature difference between present day and the last ice age. Agricultural collapse in temperate zones. Growing seasons too short and cold for major grain crops. Sunlight reduction of 70% or more. Immediate deaths, 300 to 500 million. Secondary deaths, most of human population. The physics is straightforward. Black carbon particles absorb solar radiation in the stratosphere before it reaches the surface. Unlike tropospheric particles, stratospheric soot does not rain out quickly. The stratosphere contains minimal water vapor. Particles remain suspended for years. This is not speculation. These are peer-reviewed models using established atmospheric physics, validated against observed volcanic events. The mathematics has not changed since 1945. Any system with non-zero failure probability will eventually fail. Nuclear deterrence has non-zero failure probability. We have documented 22 serious incidents in 78 years. Therefore, nuclear deterrence will eventually fail. The only question is when, and whether consequences are survivable. 80 years of survival does not prove the system works. A coin showing heads 80 times does not prove it cannot show tails. Each flip is independent. The accumulated probability simply waits. I was called naive for proposing international control. Perhaps I was. But the alternative, trusting that luck holds forever, is not realism. It is denial of arithmetic. The physics of nuclear weapons does not change. The mathematics of probability does not change. The only thing that changes is the accumulated sum. 80 years have been added to that sum. The next 80 will add 80 more.